experiment gives us this information about the cross-section. So it has a non-zero value only at a single value of the x, which corresponds to a cosine theta is equal to 0. So what can you say about the shape of the hidden object in this circle? If we know that it is a hard object, can you say something about the shape? Well, it's like a wedge. So if you just look at this one, P1 comes, it should scatter somewhere here. If it's a hard object, it should be the object, the surface should be something like this. So if you look at all the others, the object turns out to be something like that. So the shape is also encoded in the cross-section. If you look at the color, if you think of the color of the object that we see around us, I don't know, your friend over there wears a purple pullover. She's over there in the same row. So what can we say about the cross-section? How can we relate that information to the cross-section? So why do we see it purple? Because we know that light of a definite frequency, when it hits that pullover, it is scattered to us, but all the other frequencies are absorbed. So we can say that the scattering cross-section for that frequency is non-zero. For all the other frequencies in the visible range, they are zero, the scattering cross-section. If you look at the absorption cross-section, which is when you have the photons colliding with the pullover, and in the final state they are absorbed, the absorption cross-section is zero for purple color and non-zero for all the remaining frequencies. So all the information is encoded in the cross-section. Now the problem is, the main difficulty is how can we extract that information from the cross-section? In this simple example, it's kind of trivial to extract the information. Well, even in this setup, we don't know what the shape looks like over here. We have to devise other experiments. We have to send the particles from this side, such that or from the opposite side to discover what the shape of this object is on the other side. If the object is not rigid, it is soft, the problem becomes even more complicated. But nevertheless, the information is there. It is up to us to extract that information. So, now we also talk about differential cross-section. You have probably also heard about integrated to total cross-section or the integrated cross-section. As a rule of thumb, whenever you integrate over something, you are losing information. To obtain this, we integrated over all. In our studies, we had this two-particle scattering. In the final state, we have 6 parameters that we can measure. The 3 components of each one of the momenta. The momentum of each one of the particles. So that has 6 parameters. Now we are integrating over 5 of them, and only 1 is remaining. So in a sense, we are losing some information. We could have extracted more, we could have obtained more detailed information if we could study all 6 of the parameters. But in this particular case, the other 5 parameters do not really carry any information. In principle, they can. But in our case, when we are studying spinless particles, we had already argued that the scattering cross-section can only depend on one parameter. That is the only physical parameter. So by looking at that only physical parameter, we are trying to find out what causes the scattering. So what lies in the region which scatters my object? What are the processes that cause this scattering? So that is why we are always trying to find the scattering cross-section. Either using experiments, you analyze data and you try to extract cross-sections for the creation of some particles or the decay with, or decay of certain particles into definite final states. Or from the theoretical side, we try to devise theories and try to calculate these differential cross-section and study how they change depending on the observable parameters that we have. Now, if our theory predictions the dependence of our theory predictions on the experimental and the experimental observations they match, then we say that our theory is probably correct. If they disagree, for example, it might happen that in a given theory, the differential cross-section is peaked around 90 degrees. This is a theory. Assuming that this is such a triangle shape is our theory. And this theory predicts that this cross-section is peaked at 90 degrees. Some other friend of yours can come out with the theory saying that, no, it's not a triangular shape, it might be a circular shape hidden inside. And then you calculate the cross-section. Well, in this case, if you calculate the cross-section, if one comes here, it will scatter forward. If you send it here, it will scatter backward. So you see that the dependence on the cross-section on the angle of this theory doesn't match your observation. So you have these two theories which try to explain what is going on in this hidden area. And one of the theory matches the predictions of one of the theory matches your experimental observation, whereas the other one doesn't. So you just throw it away. Now, of course, you can have another theory, another one of your friends devises another model, and he says, no, it's not such a triangle. It is such a shape. So you have the original triangular model and this new model. They both agree with your observation. But then your friend says that, okay, so we will agree in this experiment, but I can devise another experiment in which I will not agree with you. So I can send the particles from this side. So then they ask their experimentalist friends to carry out this experiment and send the particles from here. And depending on how the particles are scattered, in that case, they can eliminate one of their models and keep the other one. And this way we try to refine our model. And that is always done this way or that way through calculating different scattering cross-sections or decay rates. Now, if we come back to our calculation, our lectures, we had first defined the scattering cross-section. Okay, and next week you will be spending lots of time on how to analyze data and extract the cross-section information from the data. I think. But this week, let's try to calculate it. Now, we said that when we define the cross-section, we have this matrix element squared. This is where all the physics is. And we have not studied that yet, up to now. And we have all these phase-space factors. And we are integrating over all the finite state particles. And we also have some, if we are looking at two particle collisions, we also have this flux cycle. This is what we need to calculate. Now, kinematics doesn't give us information about physics, about the dynamics of what's going on among the particles. So we wanted to get rid of them first. So we integrated out them. And what is left, what we had found was the sigma by dt. We wanted to write it in a form which is also independent of reference frames, such that our friends who do experiments in different reference frames, either one of the particles is fixed, the other one hits that, the fixed target experiments, or they can just collide in the central band, or we have also the asymmetric accelerator where the particles, both of them are moving, but one is faster than the other one. And we have shown that this differential cross-section is 1 over 4 pi m squared. So I might be wrong in the factors. 1 plus s m1 squared and 2 squared. This was more or less the expression we obtained. Now, once we got rid of the kinematics, from here now we cannot avoid anymore the physics. So we have to calculate this matrix element squared. Well, you will see in the quantum field theory courses how to extract how to write down these matrix elements in a formal way, but there are short rules. So once you accept the rules, I will not be driving the rules, but once you accept the rules, then it's just a matter of seconds to write down the contribution to this invariant matrix element. Well, the calculation of calculating that invariant matrix element is another story. It will take a long time. But just writing down the expressions kind of make the Feynman rules makes it almost trivial to write down this expression for the matrix element.
What if you don't have a stable topology for the particle? What kind of information we can get from the system? And what is the meaning of cross-section?
Well, if you have, for example, you have an ensemble of these particles, which have different orientations. Well, that makes your life hard for you.
Well, that tells you to devise a different experiment. Instead of sending your particles at larger distances like this one drawn on the table, you have to define a means of devise some means of sending beams appropriate with the shape you suspect being in the black box. That means your incoming beam should be compatible with the experimental, with the physical features that you want to measure. Was it too abstract or?
More or less.
And most of the time in physics, we start with the simplest case. Let's first assume, I don't know if you will know the joke, but let's assume a spherical chicken. Then you calculate the perturbations of the spherical chicken. Now, what were the rules? We have written some of the rules up to now. We know that whatever the theory is, in fact, if you have fermions in your theory, you can have fermions connecting to different points. These points will be what I call the vertices. And these fermions will carry some momentum, let's call it the T also. Then such an element in our graph will correspond to I E slash plus M divided by T squared minus M squared. This is the fermion. Then I have the photon, which I will show by big line like this. And this will give me, okay, the photon has a polarization. It can start with a polarization nu, and it can end up with another polarization nu. Well, if there is no interaction, this polarization, of course, will not change, so we have this factor of T nu. It carries a momentum Q squared. In QED, we also have this vertex. From a single point, we can have one fermion line entering, one fermion line leaving, and a photon line attached to that vertex. And this vertex will have the index mu. And this will carry a factor minus I. Let me write it in this form. The E, the electric charge, 1.6 times 10 power minus 19 coulombs, depending on which units you use. There's Q E side, let's say this is the fermion side. This is plus 1 minus 1, or if you are talking about quarks, 2/3, 1/3, 1 minus 1/3, this factor over here. And I have this gamma mu factor. In the calculation of the invariance matrix element, I have ingoing fermion lines. Well, this is the, yes.
What's the formula for fermion?
What is
the formula for fermion?
this one?
Yeah.
This is called the propagator of the fermion.
What does it say?
But it's kind of a measure of the probability that the fermion will move from
What's
here.
the letters?
The letter, sorry. So this is T slash,
What's
which
the slash?
T slash is Q mu, gamma mu, plus the mass of the fermion divided by p squared minus the m squared. It is a virtual particle in the sense that we had said that a particle, the form momentum of a particle squared is equal to its mass squared. So if you put p squared is equal to m squared here, you just get 1 over 0, which just doesn't make sense. But that condition, p squared is equal to m squared condition, is what we call the on-shell particle. This is on-shell, and all the particles that we observe in our detector somehow. It can be a beam in our detector or a track in the emulsion. They have to have p squared equals m squared. They have to be on-shell. But for particles which we do not observe, like this one, in this electron muon scattering case, we are not observing this photon. So for this photon, it doesn't need to be on-shell. It can be what we call, if the momentum squared of a particle is not equal to m squared, in that case we call it off-shell.
Where does this expressions come from, on-shell, off-shell?
Well, if you imagine the four-dimensional momentum space, p squared is equal to m squared. It gives you the equation of a sphere in the four-dimensional space. So the form momentum is on this sphere, the shell, or it's not on the shell. In that case, we say it's off the shell.
And for both virtual and real particles, all the conservations are false, or for virtual particles, some are not?
Now, for real particles, what we mean, the particles that we observe in our detectors, they have to be on-shell. But virtual particles, the particles that we do not observe in the detectors, which appear midway in the process and then they just disappear, they don't have to be on-shell. They can be off-shell. But we will also see cases where the momentum t can have any value, in which we have to sum over all possible values of the form momentum. But when you are summing over all possible values of form momentum, that's integrating over the form momentum, they can be off-shell, but on this shell, they will be on-shell. There will be also, in this integral, there will be also regions where the particle is on-shell.
So can this...
but the singularity is integrable there. You can integrate over that singularity.
So
the integral is fine.
Can this momentum change its value eventually? Or
so you are asking that we have a fermion over here. It starts with a value P1, and nothing happens to it, but it ends up having momentum P2. So you are saying that is it possible that energy momentum is violated?
For virtual particles.
For it, you are saying that is it possible that energy momentum is violated for real or virtual particles? But we know from general arguments that if you have translational symmetry, it cannot. Energy and momentum is always conserved.
Okay, I will ask you the hypothetical questions. So virtual particles are really there, right? We call them virtual, but there is a really photon in this process. Somewhere.
Is there?
And for example, okay, if hypothetically I can construct a really small or like thin detector, can I?
What do you mean by a thin detector?
Okay. Makes sense.
What do you mean by sensitive? I mean, if your detector detects something, it somehow interacts with the object. But this photon doesn't interact with anything. So if you are putting a detector over here, you are changing the process completely. So that comes to the question, what do you mean by real? Now you can imagine these as pure mathematical constructs. That is probably the safest way. Because what we measure, what we know, is the particles we send there and the particles we detect. We don't really know what's going on. But this model works. That means.
One question. Can we write this propagator for elastic process without photon change?
Now, this propagator is valid. This is true for any fermion, any spin 1/2 particle. in whatever process you can think of. So if we see a fermion line connecting two vertices, these 2 points, then there is this fact, whatever the process is.
Our friend used the expression that maybe not everybody knows. He said the result photon. He said the result photon.
Result?
Result photon.
Without photon.
Elastic process is not changing photon. Only one point, electron and muon, elastic scattering.
Well, this is elastic
scattering
scattering.
process.
This is elastic scattering. But if they have to exchange some momentum, they have to exchange some part. It can be a photon. It can be in this case, it can be a Z photon also, which is also possible. But the propagator is always the same for the fermion. In this diagram, we don't even need the fermion propagator because there is no fermion line connecting two vertices. There is only a Gluon line connecting two vertices.
I think he's talking about 4-point interaction of that.
One point. I mean, it's
Yes, 1 point. In 1 point. Four.
So you are talking about this process.
Yeah.
Well, here there are no vertices. There are no fermion lines connecting two vertices. So you can, well, this is the Fermi theory, which we will not go into the detail, but just to answer your questions. If you have two interactions here, two vertices, then for these fermion lines, you have the same propagator for these lines. It's the same propagator.
Sorry, I just wondered, is there any particle both on shell and off shell?
Well, if the particle can both have its p squared equal to m squared and p squared not equal to m squared, then it will exist. But a number cannot be both 5 and 3 at the same time. Other questions? Well, let's come back to our invariant matrix elements. Now, in this diagram, what we are studying, we are sending in particles, so they have to, if they interact somehow, they have to connect to some vortex. For such a diagram, we have the fermion with 4 momentum p, and it can have its spin s. We will include a factor of u, en. If we have an outgoing fermion, momentum p and s, we will assume that we will include a factor of u bar, es. Where this u bar is in fact nothing but this u dagger comes to 0. And these u's and u bars, they are like the wave functions of spin 1 half particles. They are the plane wave solutions of the Dirac equation. They are called spinors. And at least to calculate the matrix element for this process, electron-muon scattering, this is all we need. Now, at the end of the last lecture, we had written down the expression for the invariant matrix element. So we started, we have two fermion lines. There is one this line, the second line. So you can start from any one you like. Just pick any one. Let's pick this one. And for the vertices, we have to put some labels. Lorentz indices, alpha, beta. Let's just start from this one. We have an outgoing fermion line for the electron. U bar E, its momentum is P1, spin S, Then we have the vertex. We are starting from the end, going backwards. We will scroll down this one. Then we have the vertex over here. Since it's an electron, this is -1. So I, E, gamma alpha. Then we have the ingoing electron connecting to that vertex. U, E, K1, eta 1. So this is S. This S1 is the spin of the outgoing electron. This eta 1 is the spin of the ingoing electron. Then we have the other fermion line. We do the same thing. We start from the end. U bar, this time is for the mu. Its momentum is P2, its spin is S2. The charge of the muon is the same as the charge of the electron, gamma beta. And we have the ingoing muon, U again muon, K2, eta 2. So looking at all the pieces of that make this Feynman diagram, we had already written down the expressions corresponding to both of the fermion lines, but we are still missing the expression for the photon. If you look at the photon, it's connecting two vertices. It is this rule over here, and the corresponding contribution from this line is just given by this factor over here. So -I. Now the Lorentz indices are not mu and mu. The Lorentz indices of the vertices that it is connecting, but it's alpha and beta divided by Q squared. So this is the matrix element corresponding to electron-muon scatter at lowest order. This is the diagram that has the lowest number of vertices. You can imagine infinitely many diagrams, some of which we will study in the afternoon probably. But this is the lowest possible diagram. So now the task is, how do we calculate this diagram? This doesn't, it looks complicated. How do we simplify it? Of course, we need to calculate make the absolute value squared. So we have to first calculate the complex conjugate of this diagram. So if we take the complex conjugate of both sides, this is equal to E1, E1, S1, alpha U, E, K1, eta 1. This whole thing complex conjugated, and we have the complex conjugate of the other one. The alpha beta divided by Q squared. Now, before we continue about this index notation, if we write this scalar product of these four vectors Tx, we know that this is P mu, X mu, or P mu, X mu. If you are lazy and if you are working on flat space-time, you can also write this as P mu X mu or P mu X mu. But whichever way you write it, you should always understand that this is equal. This is T0, X0 minus theta. Now, you take the square of this. This is P mu X mu square. Just don't write P mu square X mu square. This is wrong. Because this index mu over here, it is what we call the dummy index. So you can change it freely. So this P mu X mu square is P mu X mu and P mu X mu. Since it's a dummy index, I change the index. Because if you write it like this, what I would understand, okay, I will just first look at it and see, okay, you are using the wrong notation because the repeated index cannot appear more than twice. In this expression, it appears 4 times. But if I try to make up some meaning from this expression, I will think that this is equal to T0 squared minus T squared, T0 squared minus T squared. Whereas the correct expression is T0, X0 minus T dot X, this parenthesis squared, which is definitely not equal to this one. So if you are multiplying 2 different terms, make sure that those 2 terms do not have common dummy indices. That is, indices that are summed over. So instead of this alpha, beta here, they are summed over. And this term also has alpha and beta, which are summed over. I will just change the name of these dummy indices because I'm interested in multiplying them. So I will just call them, instead of alpha, I will call omega, and instead of beta, I will call it delta. I can changing the name of the dummy index is just like changing the name of your integration variable. It doesn't change the result. Now let's look at only one of these complex conjugates. What do we mean by this complex conjugation? UE bar, but I will be lazy and I will not write these indices. Write the momenta and the spin. UE, gamma, omega, UE. This complex conjugate. Okay, I also have this E factors, but I can just take them out, the complex conjugation is kind of trivial. Now, if you would write this explicitly, this is just a number. But for a number, complex conjugation is the same thing as Hermitian conjugation.
Was there a problem there that you changed the indices?
Yes, that was a problem. Because when you are multiplying 2 terms, make sure that they don't have the same dummy index. So I just want to, I change the dummy index so that they do not have the same dummy index.
Because of the times fine and
Square. Now, what do we mean by, this is a matrix product, the dagger of a matrix product is just reverse the order of the matrices and take the dagger of each one. So this is equal to UE dagger, gamma omega dagger. Well, this UE bar, if you remember the definition, this is UE dagger, gamma 0. So I have gamma 0 dagger, and the Hermitian conjugate of a Hermitian conjugate is itself UE. This is what I have. Well, up to now I avoided studying the Dirac matrices. I just put them okay. We have these Dirac matrices. I didn't discuss the properties. Now I need some of the properties of the Dirac matrices. Now the Dirac matrices, if you take any Dirac matrix and take its dagger, it is given as gamma 0, gamma mean, gamma 0. This is one property of the Dirac algebra. So if I use it over here, this is UE dagger, gamma 0, gamma omega, gamma 0. Now if you take mu equal to 0, we know that gamma 0 squared is 1. So gamma 0 dagger is equal to gamma 0. So gamma 0 dagger is gamma 0. UE. But this is 1, and this is UE bar. So what we have shown here is that UE bar, gamma omega, UE, complex conjugate is equal to UE bar gamma omega UV. But there is one thing that you should know. This UE bar is this U. This spinor over here is this spinor over here. So it did change. The spinor just changed their place. That's the only thing that complex conjugation does. If I have a single gamma matrix in V. So this complex conjugation over here, the only effect will be to change the places of these two spinors. And one nice thing about being on the blackboard is I can just use my eraser and fixing the spinors. This is K1 and this is eta1. And I used to hate when my professor did this, so I had to write this all from scratch. T1, S1, this is K2, eta2, this is P2, S2. I don't have these anymore. Well, these IEs in both places became minus IE. Minus IE. I have two of them. And this is the complex conjugate of my invariant matrix element.
Why are they minus sign?
Well, they were inside this complex. I'm taking the complex conjugate of this complex conjugate of IE. I will need to multiply these elements to get the absolute square of my matrix element. So let me first take this factor and this factor and multiply them, and let's see if I can simplify it. I'm not writing m squared, the whole of m squared, but it's part of it. Let's see, I have UE bar gamma alpha UE bar E1 S1 gamma alpha UE K1 eta1. I'm just taking this factor without this IE factor. And I will also take this one. UE bar K1 eta1 gamma omega UE E1 S1. Let me also give this a name. This is L alpha omega for the electron. I will make a simplifying assumption here. I will assume that, okay, when we are talking about cross-section, remember we are looking at how many particles we are detecting and which particles we are detecting. I will assume that I don't care about the spin, the polarization of the final electron. That means when I'm counting my particles, I am summing over all the polarizations of the final electron, which is this S1. And I will make one more simplifying assumption. I'm assuming that my beam, the ingoing particles, the beam is unpolarized. So that means it contains all possible polarizations of the ingoing particle, eta1. So I just need to take an average over possible spin configurations. So since we are here talking about spin 1/2 particles, this will be just 1/2. So among all, if I consider all the particles that I'm sending, all the electrons that I'm sending to this process, half of them will be pointing in one direction, the other half will be pointing in the other direction. So that's why I have this 1/2 factor. And I'm summing over all the contributions that comes from each one of the halves.
Sorry, I didn't follow. Why did you do this sum? I didn't understand how we went from that side to this sum.
So I know that eventually to calculate the cross section, I need to multiply these two terms over there. This one and this one. Well, they're long expressions, so I just first picked up parts of it. I just picked up this term and this term, and multiplying them. So I did what I wrote over here. And of course, afterwards I need to multiply these two parts and also these terms to get the total square. And then I have this expression. I want to simplify this calculation. Well, what I could do, if I don't want to simplify it, I could stick in the explicit expression for the gamma matrices, the explicit expression for the spinors, and just carry out the matrix multiplication. That is one way of doing it. That takes a really long time to perform that. The easiest calculation is what we call the unpolarized cross-section, where we are imagining, we are thinking of an experiment in which our initial beam is unpolarized, there is no polarization information, and the final electrons that are, when we are detecting the final electrons, we are not distinguish their spin. So our detector, remember the sigma, the cross section, is more or less proportional to the number of particles that we detect. So we are detecting both spin up and spin down. So that's why I have a sum over the spins of the final state particles. And since it's an unpolarized beam, half of the particle, half of the electrons in my beam is pointing in one direction, and the other half is pointing in the other direction. So I'm just averaging over the ingoing spin. Now we will also, once we, in like 20 minutes, I will also tell you how we can calculate the polarized cross section without putting in the explicit expression over here. I will not calculate it. This takes much longer to calculate that, but it's also possible. But for the time being, let's just stick to the unpolarized cross section. Now, what simplification will this bring? Well, the simplification is that, well, let's just look at this one, this here. The only quantities that depend on the spin of the ingoing electrons is these factors over here. UE, K1, eta 1, UE bar, K1, eta 1. When you sum over the spin, this term is nothing but the K1 slash minus plus mass of the particle. So I can express this sum over the product of spinors in terms of gamma matrices. This is the simplification that this summation over the spins will bring. Well, the derivation, I will not go on, but just for the time being, just accept that this as an identity.
In the previous lectures, we have seen that in electron-positron collider, if we polarize them in a different amount, we get a better total cross-section. For instance, if we polarize electron beam with 60% and a positron with 80%, we get a better cross-section. What is the reason for that?
Better cross-section or better precision?
Better precision.
But polarization itself carries some information. By summing over all possible polarizations, we are omitting that information. The more information that we can extract from a process, the more precise your conclusions will be. So in this case, we are ignoring the information. That's the explanation I can give. I'm sure there are experimental facts that makes it easier to analyze the information. Well, this identity helps us in this case because they are side by side. They're nice. But this, if we use this identity, these two spinors are not side by side, so we cannot use that identity because these, what we call the spinors, they're just, everything that appears here are matrices, so we cannot just move them around. But what we can do is we can just write this matrix multiplication in terms of its components. So if you just remember matrix multiplication, if you multiply two matrices, and if you look at the, let's say, alpha beta component of this matrix, this is nothing but A, alpha, let's say gamma, B, gamma, beta. And you are summing over gamma. So this is how we define the matrix product. So let's come here, let's just give them some indices, matrix indices. Let's call this, I take the A index of this one. A runs from 1 to 4 because U bar is a, remember, it's a row that has 4 entries. This gamma alpha gamma matrix is a 4 by 4 matrix. So I take the AB index of that one. Both A and B, they run from 1 to 4. And I have this one, I take the B element of that spinor. And that spinor is a column that has 4 entries. I do the same thing here. I take the C element, C delta element, and the delta element of the D element, and the D element of this one. Now, once I write these in terms of the matrix components, these are just numbers. The entries of the gamma matrix is just 1, minus 1, or I, or minus I. These spinors, they are just like the third component of the momentum, which is just a number, so I can freely move them around. So that becomes alpha omega. This is equal to 1 over 2, come over eta 1, come over S1, comma alpha, AB. I start from this one because I move this one, I will move it to the end. UB, K1, K1. The D element of this one, U, E bar, K1, eta 1, the C element of this one, gamma omega, this ED element, U, E, E1, S1, the D element of this one, and then I carry this, all of this spinor in the beginning, all the way to the end, UV, or P1, S1. And I have the A element of that spinor. Now I can use this identity. Of course, this identity becomes, if I take the A element of this one, the B element of this one, this is K1 slash plus ME, the AB element of this matrix. This is equal to 1 over 2. Gamma alpha, the AB element. I'm summing over the spin of the incoming electron. This eta 1 was the spin of the incoming electron. So this is the spinor of the incoming electron. I'm multiplying the spinor of the incoming electron with its own spin. So this gives me K1 slash plus ME, EA. I have a BC from this B and C. Then I have gamma omega, C and D element. And here I'm summing over S1. If I sum over S1, again I use this identity, E multiplied plus ME, but this time it is the DA element. Now let's see what we have over here. I have a matrix over here. I'm taking the AB element of that matrix. I have another matrix here. I'm taking the BC element of that matrix, multiplying them and summing over B. It's just like this. I have the common index the second index of the first one is the same as the first index of the second one. But this is nothing but the alpha beta index of the product, alpha beta element of the product. So this is nothing but these two terms multiplied, summed over B. They give me the AC element. Over here, this is alpha. In that case, it is A, and beta. In that case, it is C. This product, when I sum over B, gives me the AC element of this product, this matrix product. Now I can repeat the same thing. I have a matrix over here, another matrix over here. I take the AC element of this matrix. I take the CD element of this matrix. The second index of this one is the same thing as the first index of this one. So this is again nothing but matrix multiplication. And when I sum over the C, I get the AD element of the product matrix. Again, the same story. I have the AD element of a matrix, the A element of another matrix. The second index of this one is the same thing as the first index of this one. So it is the same thing as the matrix element of the product matrix. But this time it is the AA element. So I have this matrix product, and I need to calculate the AA element. And remember, since the index is repeated, I'm summing over the A, all possible values of A. But AA element is nothing but the diagonal element. As I sum over AA, I'm summing over all the diagonal elements of this matrix. But the sum of the diagonal elements of a matrix is just its trace. So this product, now I managed to write it in terms of the trace of a product of gamma matrix. So now I need to calculate this trace term. Now let us study the properties of the trace of gamma matrices. We know how the gamma matrices are defined. They are four 4x4 matrices that satisfy this algebra. It is almost always written in this form, but remember that since these gamma matrices are matrices, they are matrices, 4x4 matrices, their products are also 4x4 matrices. So what you have here is in fact a 4x4 matrix. So this G alpha beta is not a matrix, so there is this identity matrix over here. It's almost never written there, but it is there. Just remember that it's always there. So what do we know? Gamma alpha, gamma beta, plus gamma beta, gamma alpha is equal to G alpha beta times identity matrix. Well, I can take the trace of both sides. So since we have an identity over here, the trace of both sides have to be equal. Well, the trace of the 4x4 identity matrix, it has 4 ones in the diagonal, so the sum is just 4. Oh, here I have a factor, sorry. Now the trace has a nice property that we will use quite often. If you have the product of two matrices and take the trace of it, it is important that there are only two matrices. This is equal to trace of BA. Or you can generalize it, trace of A, B, C, and D. This is equal to trace of D, A, B, C. So what this tells you is that if you have a product of trace, you can just move the matrix at the end to the beginning. Well, let me look at here. This is equal to trace of gamma alpha, gamma beta. Well, here I have gamma alpha at the end, but I know that I can move it to the beginning. But if I move it to the beginning, I end up having trace of gamma alpha, gamma beta. This is equal to 8 G alpha beta. Well, these two are the same thing. So trace of gamma alpha, gamma beta is equal to 4 G alpha beta. This is the trace of the product of two gamma matrices. Well, here I have the parentheses. If I open the parentheses, I end up having, okay, I have the NE squared term times the product of two gamma matrices, and I need to calculate the trace, that I know. But I also have gamma alpha K1 slash gamma omega K1 slash 4 gamma matrices. I need to take the trace of these 4 gamma matrices. Well, let's see how we will calculate the trace of the product of 4 gamma matrices. Trace of gamma alpha, gamma beta, gamma delta, gamma E. Now, the trick in calculating the traces of an even number of gamma matrices is to pick any one. Let's just pick this one. I know that gamma alpha, gamma beta is equal to 2 G alpha beta minus gamma beta, gamma alpha. If I move this to the other side, gamma alpha, gamma beta plus gamma beta, gamma alpha is equal to 2G alpha beta. That is the defining relation of the gamma matrices. I have this identity. So I can move this gamma alpha to the other side of gamma beta at the expense of such a term. And then I will first move it over here by switching the places using this identity. Then I can exchange alpha and gamma delta using the same identity once more. And then I will move gamma alpha, exchange gamma alpha and gamma eta again using the same identity. And gamma alpha will come to the end, but I know that when gamma alpha comes to, when there's a matrix at the end, I am free to move it under the trace. I can move it to the beginning. So I will start with this one, and eventually I will obtain an expression which will also contain this one. So I will have a linear first order equation to solve with one unknown. And it's easy to solve. Now let's do it explicitly. This is equal. If I exchange these two, I have 2G alpha beta. What is left is gamma delta, gamma beta, minus trace of gamma beta, gamma alpha, gamma delta, gamma eta. I just use this item. Well, this trace I had already calculated. So this was 4G delta eta. So this is equal to 8G alpha beta, G delta eta, minus, well, I now exchange this alpha and delta, twice G alpha delta, trace gamma beta, gamma eta, plus trace gamma beta, gamma delta, gamma alpha, gamma eta. I have a 1 minus over here, another minus from here. This is equal to 8 G alpha beta, G delta eta, minus 8 G alpha delta, G beta eta. Well, I will do the same trick again, plus 2 G alpha eta. Now what's left inside is a trace of gamma beta, gamma delta, but that is 4 G beta delta minus trace gamma beta, gamma delta, gamma eta, gamma alpha. So what do we see? I can move this gamma alpha to the beginning. Well, in that case, it is the same thing as the initial trace that I started with. So I obtain the trace that I'm interested in is equal to something minus the same trace. So I can just move this to the other side. So I have twice the trace of gamma alpha, gamma beta, gamma delta, gamma eta. It is equal to 8 T alpha beta, T delta eta, minus 8 T alpha delta, T beta eta, plus 8 T alpha eta, T beta delta. So this is the trace of 4 gamma matrices. Well, the trick always works. For even number of gamma matrices, you just pick the first one, move it until the end, and you end up having the trace you are interested in is equal to something that contains the traces of a less number of gamma matrices minus the trace you are interested in. So your first homework. Trace of gamma alpha 1, gamma alpha 2, gamma alpha 3, gamma alpha 4, gamma alpha 5, gamma alpha 6. 6 gamma matrices. Well, these are for the traces of products of an even number of gamma matrices. Then we also have the trace of products of an odd number of gamma matrices. They are easy to evaluate. Well, the trace of gamma alpha 1, gamma alpha 2, gamma alpha 2n plus 1, an odd number of gamma matrices, this is equal to 0. If you have the trace of a single gamma matrix, it is 0. If you study the trace of the product of 3 gamma matrices, it is 0. 5 gamma matrices, it is 0. They're all 0. To simplify my calculation of the black hole, I will assume that the mass of the leptons are 0. And it shouldn't be hard for you to guess your other homework. Review using mass of the leptons is not equal to 0. So what changes if there is a lepton 7 mass? I will neglect the electron mass, I will neglect the neon mass. Review the calculations that we will be doing after this level, assuming that the leptons are mass.
What kind of change do we expect in that case? What kind of change?
Well, the calculations might be a bit slightly more complicated. Well, if you are asking experimentally in QED, unless you are very close to the, it will not change much as long as your energy is high. But this is for me to shorten the calculation.
What would change in standard formula if the time unit would be massless?
Lots.
What would change?
Well, let's see. Let me give you an example from the atomic physics. What will change in atomic physics? Does anybody know the expression for the Bohr radius? Bohr radius of the hydrogen atom. What is the dimension of length in the natural units that we are using? in the natural units that we are using now. The length has the dimension of 1 over the energy. The energy has the dimension of the mass. So if you consider the electron orbiting the hydrogen atom, the only dimensional parameter is the mass of the electron. So the Bohr radius is 1 over me. Well, with a slight modification, there is also the alpha. So if me is 0, you don't get the atom. So you will not be here if the electron is mass. Just to say the simple consequence of the neglecting this electron mass. Now, for me, in this case at least, I will end up having a single trace with the product of 4 gamma matrices. This is what I need to calculate for this factor. Well, it's just, I had calculated over here. Of course, you need to write this K1 slash explicitly as K1 slash will be K1, let's say delta, gamma delta. You can take K1 delta out, then only the gammas remain. You have 4 gammas. You know the trace from here is divided by both sides by 2. I will just write down the result. 1 over 2. It is 4. 8 divided by 2 is 4. K1 alpha, E1 omega, minus E alpha omega, K1 E1, plus K1 omega, E1 alpha.
Can I ask something? Can we say omega here because we have one more omega?
Where?
For that?
This omega?
I mean, there in that expression, you should have alpha and omega.
Okay. Now I'm almost done. Let's write the m squared. I have the product of these two, which I denoted by LE alpha omega. Alpha the index of this one, omega the index of this one. But if I look at these terms, they're also almost this term is almost identical to this term. This term is identical to this term. You just need to change the momentum. Instead of E1 here, I have E2. Instead of K1, I have K2. That is the only change I need to have. So let us label it by the mu or the mu. And the indices it has is beta delta. And what is left? Well, I have the product of these two. D alpha beta, D omega delta, divided by Q4. This is my h squared. I know what these L's are. So if A just cancel it, here we have a factor of 2. A factor of 2 from here, a factor of 2 from here, that should be n. Or let's multiply with these factors first. Well, this D alpha beta just tells me that instead of beta, I should use alpha. If I multiply this, this just becomes an alpha. And this just tells me that instead of delta, use the index omega. Divided by Q4. So this matrix element squared is 4 divided by Q to the 4 times. Well, for the electron, I have K1 and P1. K1 alpha, P1 omega, plus K1 omega, P1 alpha, minus K alpha omega, K1 P1 Well, for the muon, they have the same indices now. The only difference is instead of K1, now I have K2, P2 omega plus K2 omega P2 alpha minus T alpha omega K2 P. Now the rest is just multiplication. N squared is equal to 4 over q to the 4. Now let's start with this term and multiply it over here. So K1 alpha, K2 alpha, that is K1, K2. Then I have K1 omega, K2 omega, K1, K2. This times this one is just K1, K2, K2, K1. And then I have this times this one, it is K2, P2. If I multiply, sorry, this is alpha omega. If I multiply that by the alpha omega, I get K1, P1 minus K1, P1. K2P. This is the first term. This term multiplying these three terms. Now let's come to this term. And let's take this one and multiply all the three terms here. I have K1 omega multiplying this one is K1 P1 and P1 K2 with a plus sign. But that is the same thing as this term over here. So that gives me a factor of 2. If I take these two terms, K1 omega, K2 omega, that's K1, K2, P1 alpha, P2 alpha, P1, P2. So K1, K2, P1, P2 with a plus sign. That is this term over here. I have a second such term. And then I have this term multiplying this term. I have K2, P2, K1, P1. So it is the same thing as this term over here. So that gives me another factor 2 over here. And finally, I have this term multiplying all these terms. Let's see. This one is K1, P1. If I multiply it with this one, it is K2, P2 with a minus sign. So this was already minus 2. I have another one, minus 3. I multiply this one and this one. It is again K1, P1, K2, P2 with a minus sign. It became minus 4 of them. And now I have this one times this one. The alpha omega, it gives me 4. Minus, minus, plus. I have plus 4, K1, P1, K2, P2. I have minus 4, now I have a plus 4, so this just goes away. So this is my n squared. Take over q to the 4, K1, K2, K1, K2, plus K1, K2, K2, K1. Now your third homework for the morning session. Express n squared in terms of S, T, and U. how you should proceed. Let's look at K1, K2. K1, K2 is nothing but 1 over 2 K1 plus K2 squared minus K1 squared minus K2 squared. This is 1 over 2 S. These are the masses of my lepton, which I neglect. So K1, K2 is nothing but S. P1, P2, I'm not holding the homework for you, but you have to put in the masses. This is 1 over 2 P1 plus P2 squared minus P1 squared minus P2 squared. Again, this is nothing but S over 2. So I have this is S over 2, this is S over 2, so S squared over 4. This is for this piece. Now, K1, K2. This is 1 over 2 minus 1 over 2. K1 minus K2 squared minus K1 squared minus K2 squared. But K1 minus K2 is what we define as U. This is U over 2. If you do the same thing for K2, P1, this is also minus. It's a minus sign. Minus U over 2. So our matrix element squared is 8 over 2 to the 4, S squared over 4, minus U squared over 4, or so over 2 to the 4, S squared minus U squared. We have our indirect matrix element, and you can just put it in the sigma, and we have the cross section for the electron muon scattering. Well, you might complain that there is nothing that depends on T over here. But remember, S plus T plus U, this is equal to 0, since we are neglecting all the masses. And this just tells us that T is equal to minus U minus S. No, or U, this U. S is fixed by our experiment. But this U is minus S minus U. And now we can go for the lights. Questions before we go?
Maybe we can recommend a little bit up, not a bit up from the grade. I don't know, 10 after 2?
But didn't you say express in terms of STU? You already did that.
Which one?
The homework sheet, then express in terms of
Yeah, but you should do it in the mass, with the mass terms.
Ah, okay.
Can I ask something?
Sure.
What was Q? Is it Q?
Q is the momentum of the photon. Q squared is T1 minus K1 squared, which is also what we define as T. There is also T dependence over here and the T dependence over here.